Hi everybody, this is a quick video to give you an overview of the topics for assignment 23, which is linear programming, kind of one of the more interesting topics we're going to cover in this course. I've heard it said that the ability to solve linear programming problems was one of the things that made a critical difference in the outcome of World War II. It was like strategically important that American manufacturers could use linear programming to optimally produce war equipment. So, well, let's get on to it. The basic idea is that you will have, actually, let's look into the MyOpen Math stuff, and this is the section we're talking about, 23, linear programming, maximization. The approach we're going to take is graphing, so we'll just do things by graphing. Um, that is only possible in problems that have just two variables. So, because you'll have an x and a y, so things are visible in the xy plane. Um, Let me pop into the videos and readings thing and open up the PDF here. So let's just take a second to review the bold things that are pointed out in this, or emphasized in this opening paragraph. Linear programming is the name of the area. It may tend to make you think you're talking about lines because of that. It's used in a different sense, actually, linear in the sense that the functions involved have a certain property that is linear. It's called linearity. Anyway, we'll have maximization problems, minimization problems, or, we can just talk about optimization, doing the best of something, which is sort of the generic way to talk about either maximizing or minimizing. So what is it that you will find the best value for? That is always known as the objective function. I'm wondering if this view is too far out here. That's better, probably. Um, and then there, you know, often if your objective function is something like the profit for a company, make and the variables might be a couple of different products that you can sell. If you just made the two values x and y for the products that you can sell arbitrarily large, you'd be making more money, wouldn't you? Well, no, because there's often in the real world something called constraints, something that limits you. I'm going to give an example in a minute of a car dealership, and it's going to be very simplified. So there'll be two kinds of cars, but the constraint in this one is going to be that there's only space on the lot for a small number of cars. That's physical, right? You can't, if you've got room for 20 cars, you can't get away with saying, oh, I'm going to sell 100 cars because you just have nowhere to put them. That's the kind of things that end up being called constraints. And you notice that word is plural, constraints. Um, it's because usually there's a lot of different limitations on what you can do. So we will maximize an objective function subject to a set of constraints. The first example is a little bit involved, but I want to show you something that's in that example right here. The fact that x and y can never be negative is often one of the constraints you'll use. Almost every time it is, because look, x and y are going to be things that are variables that count something, and it doesn't make sense if you're talking about a real thing. If you don't allow the idea of dead, negative values don't make sense. So these two guys are called non-negativity constraints. All right, so this is the standard form for a linear program. What we've got is, it tells us we're maximizing, could have been minimized, but this one's maximize. The thing we're maximizing is called I, and it's just a multiple of x and a multiple of y. Then you'll say subject to, and you'll list some inequalities, some constraints. And amongst those constraints, you see the non-negativity constraints. All right, so let me pop over to my doc cam and we'll do a small example. Um, I said we'd have a car dealership, right? So a car dealership that has two sorts of cars they can sell. So we're going to say X is the number of type A cars because, I don't have any. I guess I could make up some fancy names for cars, but I'm not going to. Y will be the number of type B cars. And our constraint is going to be that we've only got room on our lot for at most 20 cars. Now, what do you think you might be maximizing in this case? There's an assumption, I guess, that your distributor is going to send you the vehicles at the beginning of the month, and over the course of the month, you'll be able to sell them all. That might not be the case, but a lot of math problems involve these sort of simplifying assumptions. So assume we sell all the cars in the course of the month. I'd like to make the most money out of it. Now, the profit, and usually I'm going to call that P, profit is going to be how much money do we make off of a type A car, plus how much money do we make off of a type B car, except multiplied by how many of those types of cars we have. So let's say it's we make $200. Actually, I'm just going to do 2 times X because we'll know we're measured in $100, hundreds of dollars, and 3 times Y. Now, if that setup would generally be given to you in a paragraph form, and I've just sort of spoke the information while I wrote down the basic facts. Your first job is to put it into this kind of form where we say we're maximizing. It's going to be P equals 2x plus 3y, and say the word subject to and write down your constraints. So let me do that next. Give you the standard form for the linear program. So it is, we're going to maximize P, which is equal to 2x plus 3y, subject to well, there's actually 3 constraints. It doesn't make sense for the dealer or the distributor to send me a negative number of cars. So X is greater than or equal to 0 and Y is greater than or equal to 0. It's reasonable that I might not get any of the cars that give me less profit, but it isn't reasonable for me to say I've got negative number of them. And then additionally, we had that constraint about how much space was available to keep these cars on our lot. All right, that is as simple as you can make a linear program. We've got an objective function and just 3 constraints. Those inequalities create an area that looks like a triangle. So let me next show us. Hold on one sec. Yeah, forgot to transition. There we go. Let me show you using GeoGebra to set up this kind of a problem. Basically, we've got our objective function, which I would like to put it in a slightly weird way. I'm going to give you a slider. And this is something you can create off the menu system if you're on the app. A slider is, well, usually it's just given by telling you what's the minimum value and what's the maximum value. So I'm making a slider. Oh, I meant to call it something. So we'll call it P. P for profit. P equals a slider 0 to 10. And that becomes a graphical element. It's over here on the screen, but it's also available right in here. And it lets you change the value of P. So P there is my profit. I actually have a formula for profit too. So it was 2x plus 3y, and I'm just going to set that equal to p. And you see that I get a line when I do that. Now, look what happens when you wiggle the slider. This is showing me profits, what profits look like as I go from $0. Well, actually, that's in hundreds of dollars, so 0 to 10. Okay. So that's the first setup. And I may change this slider later. Like, for instance, maybe I find that it doesn't go far enough out, and I can go and click on it and change this number. Whoa, I know I can change it to be 100. It's not letting me change this number. uh, I think I might just have this thing shrunk too small. There we go. So maybe I go from 0 to 100, in which case, if I change the slider like that, I'll be able to go right off the screen with it. But, you know, we'll have to adjust that later when we see what the range of our problem is. But that's a visual representation of the XY pairs that will give us a certain profit. We also have these constraint conditions. So let me just put them in. You can say x is greater than or equal to 0. That's one. And it shades the region where x is positive or non-negative. Here's another one where y is got to be greater than or equal to 0. Shades that region. Now you should notice that the region where x and y are both greater than or equal to 0 is over here in the upper right. And that is called the feasible region, where the constraints are satisfied. Well, not quite, because there's one more constraint, that x plus y has to be less than or equal to 20. Let me zoom out a way so we can see the feasible region now. Hello. Something strange going on. I can't seem to move the graphic view. Well, okay, we'll have to... No, I really didn't want to do that. Oh, goodness. It's putting this item up in front of the view that I don't really want here. Can I change something and then it'll go away? No. Okay, well, that's what it is. It's clouding the view for me a little bit. I don't think that happens when you're using the app on your phone. Oh well. Here's the problem, and I'm going to show you a hack for how to deal with this. The problem is that no part of the screen is unshaded at this point. Everything is covered with some color. You can see the region where all of these inequalities are satisfied. It's the darkest one. So here's my hack. Just turn the inequalities around. Turn them all around. So where I had x is greater than or equal to 0, make it less than or equal to 0. Same for y. Less than or equal. And this one was less than or equal. We're going to make it greater than or equal. When you do that, the feasible region is the part that hasn't got shading on it, which is much easier to see, honestly, than the one that's shaded the most. That becomes even more important when there's maybe 4 or 5 constraints. This region can get a bit more complicated. All right, so here's the general thing you're going to do. You're going to move your value for p, and you'll notice that, wow, if we're at this point, which is 20 of the x cars and none of the y cars, that's the ones that I make less profit on. I think I'm not quite there. I believe I would be there, 40. That's actually $4,000. I'm making a $4,000 profit off of those cars. Could I have done better? Well, the fact that there's still sort of room to move this line and still stay in the feasible region tells you that you can. So here's the plan. You move your slider until you just would leave the feasible region. That's the corner where you're going to have the maximum profit. Now, in this case, actually, it's really obvious that that would be the case. You've got two kinds of cars, and one of them makes more money than the other. You should stock up your entire inventory with the one that you make more money off of, and that's the thing we're finding. Let me return to the book for a second. Oh, there we go. Let's see what the feasible region. I'm not going to go through the graphing it in GeoGebra business on this one, but they've got it graphed for us in the book. This is one where there's four constraints: the non-negativity things, that 2x plus y is less than or equal to 16, and x plus y is less than or equal to 12. Um, well, actually, you know what? Before I press on and show you the feasible region for this, we ought to come back here and notice some stuff about the words. Because this is going to be one of the harder aspects of these problems, is translating from the words that are given to the inequalities and things that you need to express. So in this, it's a slightly artificial thing. Nikki's got some part-time jobs. She calls them job 1 and job 2. She never wants to work more than a total of 12 hours a week. That turns into this statement right here: x plus y is less than or equal to 12. X and y are how much you work on the two jobs respectively. But there's this other feature that is in here, that every hour she works on one of the jobs, she has to put in some prep time. In fact, for both of the jobs, she has to do some work outside of work to be ready to do the job. Maybe she's tutoring and she needs to study the material herself before she can teach the other person. But she makes the assumption, or decides, that 16 hours is the max she's going to be willing to spend on that prep time. And finally, we've got some information about how much the jobs pay. Job 1 pays $40 an hour. Job 2 pays $30 an hour. No, not really if you count that prep time stuff, but that's where we get I is 40x plus 30y. That's her income. The total amount of hours worked is capped at 12, and the total amount of prep time work put in is capped at 16. So there you go. You get the inequality system. And this is what it looks like. It's a really kind of a coarse graph made from an old school graphing calculator, I think. But you see the region here. It's got 4 different boundary lines. So it's, what do you call that thing? A trapezoid, I believe. So here's the fundamental theorem of linear programming. And you should imagine that, I hope this will make intuitive sense to you. You get the maximum somewhere along the boundary of this region that we've just drawn, this feasible, or they call it feasibility region. I've only heard it called the feasible region before. Still, it happens at one of the corners. It can be the case that it'll happen along an entire little line segment, but that'll mean it'll happen at the endpoints of that line segment too. So what you basically can do is figure out where are the corners, what are the corners of the feasible region. Just calculate your profit, or your whatever the thing you're trying to maximize, in this case income, at each one of them, and you'll have a small list of values to select from. One of them will be the biggest, so that's the one you'll pick. Okay, well, that is where I wanted to get you for today. I wanted to just make sure you knew about that hack in GeoGebra to reverse the sense of the inequalities. That'll make seeing the feasibility region easier. And also how to create a slider in GeoGebra, because that'll make it sort of easy to just manipulate the slider to see what the objective function is doing. Okay, so good luck to everybody. I'll see you again. No, I won't. This is a virtual class. Ciao.